Can you see it now?
Yes, that's perfect.
All right. Cool, here we go. So let's talk about DEM quickly, how old is the technology and what is it about. So DEM stands for Discrete Element Modeling. It's basically been developed in '85, so it came a long way. And in its very basic form, it was spherical particles, or balls, or spheres, which were defined in space with the initial velocity, and then the solver would calculate interaction with other particles, collisions, forces, etc. This seemed like a wonderful idea at the time because mathematically it was quite easy to do spheres because the particle shapes were the same, but to use the software in reality brought a couple of challenges. First of all, no real particle performs like a sphere, so some material calibration was introduced. Um, and then some spherical clusters was introduced to make all of this accurate. Um, and then we also had to do some rolling resistance to make this ball act like a rock, whether it's long and slabby or big and blocky. You had to do a whole bunch of things to get the simulation to react properly. Then luckily we've got the Rocky guys or the ESSS guys coming through and introducing a real shape particle simulation. Just a quick comparison between real particles and glued spheres. The code implementation for spheres is obviously more simple to implement because you're sitting with the same particle size, and it's very easier to find centroids for glued sphere particles. Um, the friction was always the issue with spheres because you would essentially have contact points of the particle with the boundary surfaces, where with polyhedral or real shape particles, this will be very accurate. The aspect ratio was also one of the challenges in spherical DEM, where with real particles we can have any aspect ratio. And then the last challenge was breakage. You couldn't really break spheres because you are confined to spherical particles. So you could only introduce another spherical particle, where with real particles, we can break it in different ways. Now, this video was the first video I saw about of Rocky back in 2011. And this really got me excited about the world of DEM because they could combine all these real particle shapes and get that kind of simulation. We've been used to spherical DEM for a number of years, and it was also very difficult to solve these large problems with millions of spherical particles. Rocky also introduced something called GPU solving, and I'll say a little bit more about that on another slide. But the main limitation for any DEM technology always has been computational power. And the more particles you put into that simulation, the more equations needs to be solved, and the longer the runs could be. And this could take months, just 5 years ago, which we can solve now in minutes and hours. So inside Rocky, there's a couple of particles. We still have spherical particles that you can use to maybe approximate fines in your simulation. Sometimes you do have spherical particles that you want to simulate, but Rocky does have a particle library that you can choose from standard library shapes. And then you can also import particles from CAD. You can even scan particles, and then Rocky will simplify the faces to get a representative particle in the simulation with less faces, because remember, each face is an equation that needs to be solved. And then recently they've introduced particle assembly, where you can take standard library shapes and assemble the particles together. This is a very powerful feature because it makes the solver perform much, much quicker. Other types of particles available in Rocky, and this is differentiating Rocky, I think, from any other DEM code, is we've got flexible fibers also as a particle shape. We can do various kind of shells and concave and convex solid particles.
Just a note on that, Isak. I think one thing that is beneficial of having these different shapes is it opens up a couple of different industries for us. So obviously, mainly we still apply it in a mining perspective, but we have done some work, for instance, recently for guys that are doing sugarcane processing equipment with the flexible fibers, and that's also quite an interesting application. And I think there's quite a bit of cross-population of ideas that can happen between the agricultural, the pharmaceutical, and the mining industry. And having us all use the same tool actually makes that quite more possible, I think.
Yes, absolutely. And I mean, if you just think, if you had to build a fiber with spherical particles, you would need to assemble a string of spheres together, and that will be completely inaccurate, which makes the material calibration a lot more. And I think that's one advantage of simulating real particles, is that your calibration becomes a lot less, because you don't have to make a ball act like a rock or a fiber or a shell anymore. Um, you basically have to do an angle of repose test, and that's where you take a bunch of material in the cylinder, and you lift up the cylinder and see what the angle of repose is. You'll build the same simulation in Rocky, maybe a friction test to get the accurate friction, which basically entails putting a bunch of material on a steel plate and starting to angle that and see at what point it starts sliding. And I'll say something about stickiness and adding a couple of other things later in the presentation. Just a roadmap of where Rocky came from. So ESSS acquired Rocky from Conveyor Dynamics back in 2011. They introduced particle shapes, and then the first major development was breakage. We could introduce some breakage, and I'll show some examples later. Then there was native GPU solving. Now, I want to say something very quickly about that. You have to basically rewrite the solver to do GPU solving. A GPU solver or processing unit accepts a different type of input than a CPU processor. And that means that if you have a code that's matured on a CPU solving, it's not as easy as just to apply that to a GPU solving unit. You have to literally write a translator to convert the code from CPU solving to GPU solving, and that's where ESSS did a wonderful job to rewrite the whole code to be solving native on GPU. Then in 2016, they worked a lot on multi-physics integration, both within Rocky as well as with tools like ANSYS, CFD, and FEA. 2017, we've seen multi-GPU, and then they started optimizing the solver for flexible particles, introduced some coarse grain modules to accommodate more particles in the simulation. And then in 2020, there was a lot of work done on the API interface so that you can do some manipulations to particle properties, the solver, etc. And then 2021, we had an enhanced HPC again, where we saw a dramatic increase in solver efficiency. And then recently, the SPH DEM edition, which I will show a little bit later in a slide. Let's quickly talk about materials now. Traditionally, with DEM, you would do a lot of calibration, and some spherical DEM codes has got material libraries available, but this is very dangerous in my opinion, because the coal in South Africa is a bit different than the coal in Brazil, and you have to look at each material for what it is. So Rocky has got a material and calibration wizard that help you to set up your materials, and it will give you examples of which calibration tests to do. It will help you to plot those points out and get your material data accurate.
So just a note on that again, Isak. So the material wizard that is new in this version, that'll actually give you, like you were saying, it will give you it will give you rolling resistance and adhesive values for a required angle of repose. But some questions that we have received in the past is instead of just having a tool like the material wizard that gives you direct values that could work for your possible setup. We have also had people asking a lot about having pre-made setups for different types of experimental tests that are commonly used for calibration. And this can actually be downloaded from the Rocky customer portal. There's a material calibration suite on the portal that is it's a set of simulations that have been set up that coincide with commonly used experimental methods to test materials and do material calibration. So users can log into the customer portal and download the suite and have ready-made simulations to actually do the material tests without having to set that up manually.
Yes, great. Thanks, Wynand. Wynand, we need to explain the next slide for me a little bit as well. So Rocky uses two different, just waiting for the slide to advance. So there's two different breakage methods that Rocky uses. Both of these methods works on the amount of energy that a particle will see throughout its lifetime in the cycle. It's not just the impact braking where if the collision force exceeds a certain value, it will break. It looks at the total energy. And maybe, Wynand, you can share a little bit about the ABT10 method and the Lattice method.
Yeah. So both of these methods can be used for breakage and Rocky. It just depends on what information you have available. Now, the ABT10 method is the method that was built into Rocky first. It's the older of the two methods that have been used in Rocky. And ABT10 is generally something that is used quite commonly still because of the fact that many material set information sets will have the A and the B coefficients defined based on graphs. So it's quite easy to get that information. But the main difference is that ABT10 is slightly more accurate if you have a relatively high impact energy, where the Tavares method is slightly more accurate if you have a lot of very small impacts that eventually causes your particle to break by attrition. So that's the main difference. And then the way you calibrate them is slightly different. So the ABT10, I think, you can get away with doing slightly less experimental tests to actually calibrate your model for ABT10, while Tavares actually requires quite a strenuous experimental process to get the coefficients. But there's actually a full paper published on the Tavares method and the exact tests that have to be done for that. But yeah, that's the difference between the two methods in a nutshell.
Cool. One thing that's very valuable to our clients using Rocky is boundary surface wear. Now, there's two ways that we can do boundary surface wear. The first way is the first video I'm showing there, where it will give you a representation of the impact forces on the boundary surfaces. And that will immediately give you an indication of where the high wear areas will be. And if you got things like dead boxes in a chute, for example, you can position those to eliminate high impact on the side plates or the surfaces. The second way to do boundary surface wear, and some of our clients use this, is to eat the geometry physically away and get an idea of how the boundary will look like after a certain period of runtime. This is accelerated wear simulation, so you give it a wear rate and then run the simulation for a period of time, and it will give you those results after a certain time on how the layer will be worn away. We had great success with this with some local clients, especially in the mill industry, and to duplicate those geometries with Rocky and validate that against real field tests. One thing that's very powerful included in Rocky, this is not coupled with any other exterior tool. Rocky includes a Lattice Boltzmann airflow solver. And what this basically will do is it will calculate the acceleration of the air around the particles and give you an idea of where the dust, for example, would go. It will not be able to do a sprayer on there. You would need to couple that with CFD, but this gives you very valuable results if you have to look at controlling the dust around chutes and transfer points. This is a great addition to Rocky. We've been talking about this for a couple of years. There's a very old technology called SPH, and it basically treats the fluid as particles. and it's very efficient to solve these kind of multi-phase DEM problems. In the mill industry, this is very good for slurries and to add fluid to the mill. For example, my next slide has got a very clear representation of the difference between the two approaches with a low slurry and a high slurry fill. And we could never do this. We always had to couple this with Fluent. This is now natively inside Rocky. So you don't need to buy any other CFD tool to be able to do this. This is included.
The other benefit of the SPH is that since there is also spheres and essentially representing the fluid with particles, it scales fantastically onto the GPU. So,
Yes.
so usually for these coupled problems with the SPH method, you will get an answer significantly faster than with the CFD DEM coupling. That's not to say the CFD DEM coupling isn't useful anymore. There are many cases where the complexity of the flow is such that would require the proper full CFD coupling. But for simpler cases, especially mill type cases and so forth, the SPH method is significantly faster.
Yes, I think once again, that's I'm very excited about Rocky building this into their own solver, because they could tailor it exactly to run perfectly efficient on a GPU solving unit. One very powerful feature inside Rocky is a multi-body dynamic solver, and this is built into Rocky. We're doing a very advanced simulation there, as you can see. There's particle interaction, breakage, and then the full body dynamic solver. It's actually, I think this is a simulation for looking at some certain diamonds that doesn't need to be braked, or you don't want to break them preferably. Sometimes you do, I suppose. And that little breaker is moving up and down as it hits the bigger particles. The multi-body dynamics solver is very powerful inside Rocky. You can collect all kinds of forces from this spell, and then take that over to your FEA tool to look at stresses, etc., inside the structure. Then they've added something recently, contact network visualization. This is for a compaction problem. This also opens up a couple of other industries for us, where companies need to look at how particles are compacting together. This can be from the food industry straight through to civils, etc. And this is this is a very powerful feature. You can imagine how difficult it would have been to solve this a couple of years ago without this technology. And then I want to say something about CPU versus GPU solving. Now, GPU solving, everybody's talking about it. And as I mentioned before, you have to present the data differently for GPU than for CPU. And this is an area that Rocky invested a lot into to get this running optimally. This is some data for a sample problem, I think with 10 million particles, and they solved the same problem on an 8-core Intel CPU, which completed in 12.5 hours. And then they benchmarked this on a couple of GPU cards, and you can see the speed up there is tremendous. Now, a GTX 980 is a pretty old gaming card. I think the new ones is GTX 2180 Ti or something is the new ones. And they are even faster than this, but you can see the tremendous speed up between CPU versus GPU solving. And this makes it really possible to solve very large simulations on Rocky. You can also couple multiple GPUs together for very large problems. There is a limitation where you really need a lot of particles to make this worth it. If you've got a simulation with less than 1 million particles in the simulation, I don't think that multi-GPU is going to give you that much of a speed up. But if you're talking about larger simulations, it definitely makes a huge difference to be able to do this. I don't know if Daniel Bennett want to say something about the GPU cards. I know you're using something that's affordable with really good results.
Yeah, so it is. There's actually, we could have a half an hour to 2 hours discussion just on which GPUs to solve and when they're efficient and so forth. But the first thing I think that you said that is very important, Isak, is that if you have let's say less than 1 million particles, you should only be using one GPU card. I don't think you'd get a massive benefit from scaling. One GPU will still be faster in most cases, depending on the GPU, than a CPU though. So it would still be beneficial to have a single GPU for even smaller cases. And for the actual cards that are beneficial, it actually depends quite heavily on if you're simulating spheres or if you're simulating shaped particles, because the spheres use a single precision computing speed from the cards, while the shaped particles use double precision. So in a nutshell, you can summarize it as that spheres will solve faster on gaming cards, while shaped particles will solve faster on more high-end computing cards like the V100s, the T100s. But even still, even though the gaming cards are optimized for your spherical simulations, they will still be faster than most CPUs, even for shaped particle simulations. So we have a couple of computing cards at the office, but our laptops have, for instance, the RTX 3060s, and they are still quite substantially faster than, for instance, running on an i7 CPU. So even on the gaming cards, you get quite a bit of speed up above general CPUs on those.
Yes. Good. Then the next part of this presentation is quite exciting. There's a very tight relationship between ANSYS and Rocky. And I think the reason for it is that Rocky serves the DEM technology, and ANSYS is really the best-in-class solver for CFD, FEA, and a whole bunch of other things. So you can couple your Rocky simulations within ANSYS Workbench to FEA and CFD analysis. You can link results up, take inputs or outputs from Rocky into input for CFD, vice versa. There's several strongly coupled simulations where it will solve the iteration DEM and an iteration CFD, which is very beneficial because you can solve the CFD iteration on the CPU and the DEM iteration on the GPU, and you'll get a very efficient simulation. I think one of the most common couplings that we see in South Africa is mechanical coupling, where we take some forces and some data from Rocky and apply that to FEA analysis. We can also do this transiently, so that will give you an idea of the impact forces that your equipment will see under certain particle loading. And then I think the applications for CFD coupling is very wide, and there's almost none applications that I can imagine that we can't couple together, as far as particulate flows go. A couple of examples there: cyclone separators, dryers, filtration, fluidized beds. Particle transport is quite impressive. I'll do something in the next slide. And then slurry mills, solid suppression and spray coating, and more for the pharma industry. So, Wynand, maybe you want to say something about this beautiful video about that particle transport.
Yes, yeah. So this is actually making use of quite a efficient new feature when it comes to CFD and DEM coupling. I'm saying new, but it's been in for a year or so. But essentially, how the CFD DEM coupling works traditionally is that you need to have the DEM represented in the CFD solver as an Eulerian phase, which means you have to have a multi-phase Eulerian problem in the CFD, which can be unstable and is usually quite slow to solve. But what Rocky have done is they've implemented a new way of representing the particles as a porous zone, or a dynamic porous zone, instead of a separate Eulerian phase, in the case where we only have a single phase fluid. So if you have, for instance, only particles in water, instead of running a full multi-phase CFD simulation, you can run a single phase CFD simulation, and Rocky will send the particle information over to Fluent and create a dynamic porous zone with it. If you do have multiple fluids like air and water, you still need to represent the particles as a phase, as an Eulerian phase. But for these single fluid phase problems, running this simulation where Rocky uses or represents the particles as a porous zone rather than a phase is substantially faster again, and it's very stable to solve as well.
Right, then one of the, I think the simpler couplings is just a one-way transient coupling with Fluent. There's a nice two examples there: a dry powder inhaler and a wastewater pump. Um, we get a lot of requests for these kind of simulations on how to do them here at QFIN in South Africa specifically, because I think this was never really possible to do this. I mean, if you look in the last 5 years of cases that we've seen from our clients, and some that was inquired on for us here at QFIN, it's definitely increasing to couple these two technologies together. It is quite. It can be a complex simulation sometimes to do the CFD, the DEM coupling, but the results is very valuable to especially to the mining industry. Then ESSS worked really hard to get the Rocky interface to what we know today. It's very intuitive, it's very user friendly, and if I can maybe say something about our training, so the Rocky training is 2 days. That's all. You only need 2 days training to be able to operate Rocky. The user interface is very user friendly. There's a tree on the left hand side with some parametric things you can change, you can resolve. There's very nice feedback while it's busy solving. You can actually see what's happening while it's solving. And then the post processing is very powerful to make nice videos and use that even for marketing if you want to. Give that to the sales guys and they'll sell your equipment for you with these videos. So that's maybe another interesting use besides just the mechanical design application, is to make some marketing videos for your equipment, make sure that they work without giving away too much IP. Then recently, ESSS worked really hard on automation and customization. I think Wynand can elaborate on this. In the past, we worked very hard to do some Python scripts, etc., for certain clients to get things right. And this is now all kind of possible within the Rocky interface. Wynand?
Yeah, so essentially there's two layers of automation that can be done within Rocky. So we still have the Python scripting, which is used to automate things from a pre-processing and a post-processing point of view. So anything that you can do in the Rocky interface can be automated with Python scripts. And you can do recordings of what you are doing in the Python interface to actually have a script that you can open and modify. Or if you know the interface quite well, or you know the commands for the interface, you can actually do a lot of automations by using for loops and running commands automatically and so forth. So that has been in Rocky since Rocky 3. But they actually also have recently implemented scripting for a solver point of view. So we can now, by using some C++ scripts, we can actually change what the solver is doing in the background as well. So that can also be useful for automation of specific particle processes, but we can physically change the solver or give information to the solver or give particles additional scalar values that we are measuring while they move through the system. So with the Python and the C++ scripting, we actually have a lot of access as a user to automate things and to customize things as we need them to be for our specific simulations. It might sound a bit complex, all the Python programming and C++ programming. So it's important to note that it is not required to have any knowledge of this to use the software for general applications. It can just make your life a bit easier if you automate stuff. And if you want to do some very specific non-standard things from a solver point of view, you need the solver scripting.
Right, I want to enter our presentation, Wynand, with a quick discussion about, and I didn't prep you for this. I just think it's a great idea to talk about a couple of examples on where we saw clients start with DEM simulation and where we are at today. Maybe just a couple of examples. I don't think we need to use names of who's doing this, but I think the wonderful thing about selling Rocky for me since 2011, in the beginning we did a lot of shoots. I think that's one very valuable asset to have if you are designing any kind of shoot, is to make sure that these shoots doesn't block. There's one specific client I can name who's been with us from the beginning, and that's Henk Brink from Cedo Tech. I'm sure he won't mind the marketing, but And one thing to mention with that is that Rocky is still not a magic wand tool to any engineering company. You need a good engineer, and DEM is a tool for that. And I think Henk Brink is one of those examples where his experience in chute design and solving problems with chutes is just so wide that Rocky is merely a tool for him to verify what he can predict by experience. The value in having Rocky for an engineering company that's doing a lot of shoots is to educate younger engineers on why certain decisions are made. It's very easy for a young engineer to do a simulation and see, okay, my idea won't work because the physics doesn't match up to that. But we're still doing a lot of shoots. I mean, that's one of the most common inquiries we get is people who needs to design a shoot for the first time, or maybe they're having some trouble with some of the shoots they designed. So that's one application. Then we also got a lot of vibrating screen companies using Rocky, and it's a great tool for that, especially because you can look at the loads that is being transferred to a FEA simulation, for example. Um, then I think some of the more advanced applications is where we're talking about breakage. We did some stuff with cone crushers way in the beginning, about 6 years ago. Also with some jaw breakers. Recently with Weir, they presented at our user conference. That's why I can use their name in this presentation. That was beautiful work done. We also did some stuff with Weir on magnetic separators to take some of the steel from the conveyor belts. So it's all mostly mining. I think, Wynand, if you can think about something more interesting than shoots and screens and
It
conveyors.
is. I mean, it is definitely mostly mining locally, right? Because that's our biggest market. But like I said, we have been branching out into other industries. We have had some discussions with people in the sugarcane industry, and we were having discussions with some pharmaceutical people. And I think the main thing that it comes down to is it's not just the increase in functionality that is allowing us to do more with the software, right? So if I just think about our mining clients in general, the size of the problems that they could solve 5 years ago versus the size of the problems that they can solve now, due to the increase in simulation speed because of GPU solving and just general efficient solver, is where I think a lot of the advanced usage has come from, right? Because a couple of years ago you couldn't go too big because you'd wait a couple of days for your answer, or even a bit longer if you were going really small. But nowadays, if I look at the things that come in for support, or the type of consulting that our clients are quoting on, or that we are looking at, it's not just a simple shoot where we use massive particles just to have it solve in a feasible amount of time. There's some complex things in the simulations. There's breakage in the simulations. There's small particle sizes, complex particle shapes. And the reason that we can do all of this is because obviously the functionality is there, but also because of the solver efficiency. So I think just in general, people have started using the software more broadly because you can actually now get these answers in a
Yes, I
feasible
think
amount of time.
just to add to what you're saying, I think one trend I'm definitely seeing is that 10 years ago, simulation tools was given to one engineer in an office somewhere with a closed door, and he had all these fancy tools, and he was just doing simulation. Where we see today that actual designers in the design office are actually using Rocky tools to do problems and make sure that whatever they manufacture goes out right to plan. We've done a lot of mill stuff, ball mills. We've done a whole bunch of coupling for them, especially CFD DEM coupling before the SPH was available. Yeah, and then general just material flow, just looking at transfer points, how to feed a vibrating screen material so that it's more efficient. And I think that there's a lot of value on to see how the material is performing throughout the transfer points in a plant, for example.
Yes.
Yeah, I think there's a couple of there's actually a lot of examples on the Rocky website. If you go to the Rocky website, just search for Rocky DEM on Google, you'll straight go to EEE's website.
Don't forget the DEM part. It's important.
Yes, don't forget the DEM, because Rocky will give you a guy running up the stairs with his arms in the air. There's a lot of examples there in every industry. You can browse through them. If you have any questions regarding the software, you're welcome to email me or Wynand, anybody here at QFinSoft. And I thank you for your time. Anything you want to add, Wynand, or can we end this webinar?
No, I think that summarizes it quite well. So yeah, I definitely think if anyone has questions, they can mail us, like you said, or they can link them in the comments to the video. Yeah, and then we can take it from there.
All right, cool. Thanks for the time. Thanks, Wynand, for joining me. And we'll see you in the next mining webinar about DEM. Have a great day. Thanks.
Okay, bye.
Cheers.